I want to show you a cool toy that we've made in the physics department, which might find its way floating down a railway track somewhere near you in the not too distant future. We've made a superconducting magnetic levitation train, or a maglev. So, in other words, we built a hoverboard. Here it is, a tiny lump of superconductor, cooled down to almost minus 200 degrees, shooting around a track made of extremely strong magnets. The only force slowing it down is air resistance, which means it can zoom around very quickly for quite a long time before it comes to a stop. So, how does that work? Superconductors are a strange kind of material. At ordinary temperatures, they're usually fairly boring, either a regular lump of metal or, like this black stuff, ceramic, rather like a teacup or a bathroom tile. If I take this piece of superconductor and put it near these extremely strong magnets, nothing happens. And the reason is that all the superconductors we know about so far only work if we cool them down to extremely low temperatures. So here I've got that same piece of superconductor, but cooled down to minus 196 degrees in this liquid nitrogen. So if I can just get it out, there we go, and bring it near these magnets again, you can see something rather different happens. It's just floating there, and there's no strings. I can pass the tweezers above and below. This strange property is called the Meissner effect, and it only works when the superconductor is nice and cold. So as you can see now, it's just starting to warm up. And the superconductor falls back onto the magnets, doing absolutely nothing, just like it was before, a boring bit of ceramic. The reason the superconductor can float is related to its name. It has absolutely no electrical resistance, and so it's super at conducting electricity. If you think of an ordinary good conductor, like the copper that's used in the wires inside your house, that does conduct electricity quite well, but the electricity isn't flowing smoothly like water through a pipe. The electrons are bashing into the copper and losing energy, and causing the copper to heat up. When a current travels through a superconductor, it goes around completely smoothly without bashing into anything, and that means that it doesn't lose any energy. In fact, you can start a current going round in a superconductor, and it'll keep on revolving forever and ever and ever. When the superconductor is brought near to a magnet, a current starts to flow inside it, and that current will always be set up in such a way as to create the same magnetic pole as the magnet it's brought near. So, say it's brought near a north pole, another north pole will be set up inside the superconductor. It acts a bit like a magnetic mirror. The two north poles repel, and thus the superconductor can defy gravity and levitate, and the current that's keeping it there will flow forever and ever, so it'll just keep floating. Well, until it warms up at least. So we could use this effect to make our maglev train. We can get the superconductor and just pop it straight onto the track. But sadly, although it floats nice and high, the Meissner effect only repels the superconductor from magnets, and so it's not very stable. So actually, we're going to cool it down a slightly different way. If we cool the superconductor while it's in the field of the magnets, that means that it memorizes the magnetic field that it's sat in. This is called flux pinning. And by pinning these lines of magnetic force, these lines of flux, the superconductor memorizes this position and doesn't want to move either horizontally or vertically away from it. So when the nitrogen stops boiling, we can just pull out the supports, and as you can see, the train is floating. But this time, it's a lot more stable. It's fixed in this position above the track. So we should be able to make it go quite a lot faster. Here I've got a short length of track, and I can show you that most impressively, it actually works upside down. This stuff has some pretty amazing properties, but it also has disadvantages. Firstly, as we've seen, you have to keep it very cold in order for it to work, which can be both expensive and something of an engineering challenge. And secondly, the ones of these that work at the highest temperatures, like this stuff, are ceramic, which means they're very brittle and hard to draw out into wires.